Hello everyone and welcome to day 33 of the Jamb Physics in 40 Days series. We want to say a big thank you to all of you who have made it a point of duty to always come on this series daily. I want to say thank you for checking out the videos, thank you for liking, thank you for sharing, and please, if you're yet to be subscribed to the channel, kindly take a moment to hit the subscribe button and the notification bell icon so that you get notified every time we put out a new video. And if you're new to this series, if you are seeing the video for the very first time, well, this is Jamb Physics in 40 Days. It's a series that is brought to you by Learn, where we believe that when you dedicate within 30 to 45 minutes of your time daily, you should be able to gather all the necessary skills and tools that will help you ace Jamb Physics. So if you're a candidate who is preparing for the Jamb exams and one of the subjects that you have selected in your subject combination is physics, then trust me, these videos are specifically made for you. This is why it is important that you do not miss any of the videos in the series, because what we have done is that in each of the videos, we take a look at the individual topics that are in the Jamb Physics curriculum. We do a breakdown of the topic. We tell you what is expected of you by the Jamb board, and then we also solve past questions on those topics. Now, while we solve those past questions, we also give you tips that will help you solve that question and even questions like that with greater accuracy. So it is important that you check out all the videos in the series. And please, because we want to reach a wide range of audience, we are also pleading with you that as you check out the videos, that you also take out some time to share the video on your timeline. You just don't know, you might be sending it to someone who also needs this series. So help us by sharing the videos, by liking the videos. And if you are not subscribed to the channel, please take a moment to click the subscribe button and also hit the notification bell icon so that you get alerted every time we put out a new content. And to make your practice even more fun, let me introduce you to the Exam Fun app. The link to download it is in the description box of this video. It is an app that is created with you in mind because we want to ensure that your study time is not a drag. We want to ensure that you enjoy your study time. That is why the app is created to be a game-like setting where you solve questions on any subject of your choice in different levels while you earn points and even get to earn some money. So I tell you, it is both exciting and rewarding. This is why you do not want to miss it. So please click the link in the description box to download the Exam Fun app today. And believe me, you are not going to regret doing that. So let me say thank you in advance for following those prompts. Now, to get to the business of day 33, what we are looking at today is magnet and magnetic field. Now, this topic, there's a variety of things that is expected by the Jamb board of every candidate. I've listed the topics here, so let's go through them one after the other. Now, the first thing is you should be able to identify natural and artificial magnets. That is, materials that are magnetized already, as in natural objects that have magnetic properties are called the natural magnets, while the man-made ones, that is, objects that have been magnetized, are what we call the artificial magnets. And then you should also be able to mention the magnetic properties of soft iron and steel. By now, you should understand that when it comes to soft ions, they can be easily magnetized and at the same time easily demagnetized. So which is why they are suitable candidates for when we are talking about temporal magnets. Steel, on the other hand, cannot be easily magnetized, so which is why when it gets magnetic, it becomes difficult for it to lose that magnetic property. So they are more suitable for what is known as the permanent magnet. Now, another thing is you should be able to explain the methods of making magnets. That is, how you magnetize an object and how you demagnetize an object. I mentioned some of the methods here. There's the stroking method, there's the electrical method for magnetizing an object. And then to demagnetize, there's the heating method, and then there's the hammering method. You should also be able to explain the concept of magnetic field, that is a region of space where magnetic force is experienced. So when you place any object within that field, it is under the influence of the magnetic field that is within that region. So you should be able to explain that concept including the magnetic line of force. Which is why the next one is that I should be able to explain the magnetic field around straight current carrying conductors. I should know that they form circular field around it, and then when it comes to the circular wires, they form concentric circles. And then for the solenoid, it's the same thing as what you experience in bar magnets, only that it is stronger at the north and the south poles. And then they expect that you should be able to explain the properties of Earth's magnetic field, the north and south poles, the magnetic meridian, angle of dip and declination, including the instruments that are used for measuring the angle of dip. You're also expected to be able to solve questions involving magnetic flux and magnetic flux density. And then you should be able to give the variation of magnetic field intensity over Earth's surface as it changes because of the shape of the Earth. And then finally be able to explain the applications of magnets and magnetic field, especially when it comes to the Earth's magnetic field. In the case of navigations by sailor, how they take advantage of the Earth's magnetic field to be able to find their location every time. And then you should also be able to explain how it is used in mineral exploration. Now, these are the subtopics that we find under the topic of magnets and magnetic field. Now, this video is for the purpose of prepping you for Jamb, but if you want greater details rather of this topic, we have another video on magnets and magnetic field also on the channel. Please take a moment at your free time to check out the video. Now, in that video, each of these subtopics are explained with greater details, while we give examples where necessary and also show you some pictures of some of these things so that you can identify them when you do see them in the field. So you can check out the video to help you get a full understanding on the topic. However, now we're going to be looking at past questions on Jamb, on magnets and magnetic field. And also please stay tuned, because while we solve those questions, we'll also be giving you some tips that help you solve that question and other questions like that with great accuracy each time you find a question like that. So you just can never know. During your own Jamb exam, you could be seeing the same questions we are solving right now, or the tips we are giving can give you a hint to solve questions like that when you find them during your own exam. So you don't want to miss this. So please get your materials ready, and then let's solve some questions on magnets and magnetic field. A magnetic needle is suspended first at the Earth's north magnetic pole and then at a point on the magnetic equator. The respective angles between the needle and the horizontal are, now we are looking at it with the horizontal, not with the vertical. So that's the first clue in this question. And then the second clue is that the beginning is that it was first at the Earth's north magnetic pole. Now, what happens to the magnetic needle is that it always aligns with the magnetic field at the location where it is. Now, at the north pole of the Earth, the magnetic field is vertical. So because it is vertical, the magnetic needle is going to point downwards, which is 90 degrees with the horizontal. Remember, the question says we have to measure record the respective angles between the needle and the horizontal. So if the needle is pointing downwards, that means it makes 90 degrees with the horizontal. That is at the first location. Now, at the second location, that is at the equator. So at the equator, the Earth's magnetic field is going to be horizontal. So at that point, when the needle aligns with it, it's going to also be horizontal with that field. And if you are measuring the angle with the horizontal, that makes it a 0 degree. So we see it's 90 and 0. So don't forget that the magnetic needle will align with the magnetic field at the location where it is. So at the North Pole, it is 90, while at the equator, it is 0 degrees with the horizontal respectively. So the correct answer here is option D. A coil X is moved quickly away from the end Y of a stationary metal bar, and the current then follows in X as shown above. Now, when we look at what we have here, we have a metal bar moving in this coil, and it is moved with the direction that we see here. And we see that a current is induced here according to Lenz's law, which opposes the direction of the movement of the magnet. So you see now that this direction is anti-clockwise. That's the important part now. you have to be very you have to put this into consideration when you are picking your answer. The direction, if this were in the opposite direction, which is the clockwise, it would have changed the entire answer to this question. So because of the direction here being anti-clockwise, it means that a knot is set here, which is going to make this attract the north pole. So definitely this will then become the south of the magnet. So for this, because of the direction, y is going to be south, x is going to be north. And when we look at the options, we see that the bar is not a magnet. That's wrong. Y is the north pole. No, it is x that is the north pole. And then C says y is a south pole. So this is the correct answer. So we go with option C. The Earth's magnetic equator passes through jaws. Then we have options such as angle of variation is 0, magnetic declination is 90, angle of dip is 0, horizontal component at the Earth field is 0. Now options A and D are outrightly wrong, and option B would point to either the fact that the direction of the magnetic field is either directly east or directly west, which would also make it wrong. However, at the equator, one thing that we know for a fact is that the magnetic field of the Earth is going to be on the horizontal at that point, which means the angle between the magnetic field of Earth and the equator is 0 degree. And that is what is used to describe what we know as angle of dip. So that means that the angle of dip of Earth at that point is 0. So the correct answer here is option C. When the downward current flows in a straight vertical conductor, the direction of its magnetic field at a point due north of the wire is. Now, what we're going to apply here is the Fleming's right-hand rule. Now, because the current is flowing downward, now we're going to point our thumbs downward like this. So when you do this, you see that your thumb is showing the direction of the current, which is downward, and then the other fingers that is wrapped around like this shows the direction of the magnetic field. So when you pick any point due north, you can find the direction of that magnetic field at that point. So basically you're going to have the wire like this, and then the field around it like so. Okay, now at a point due north, you find that the direction is this way, while due south, direction is this way. So this is the direction of the magnetic field, and this is the direction of the current. So since the question says at a point due north of the wire, we're going to look at the magnetic field at this point, and you see that it is going towards the west. So as a result, the answer here is option D. In the diagram, if the south poles of two magnets stroke steel bar, the polarity at T and V will respectively be. Now, when we look at the diagram here, we see that the south pole is stroking this, thereby magnetizing the steel bar. Now, as the south and south stroke this middle part here, it's going to magnetize this, and it's going to take the inverse of the pole here. And according to the rules that guide when you are using stroking to magnetize an object, what happens is that the last part that is touched by that pole then becomes the inverse of that polarity. So since this is south, and the last part that is going to be touched is going to be the tip of this steel bar, that means it's going to take the inverse polarity of south, which is north. So that is both T and V would then be north and north. So the correct answer is option C. Which of the following does not use magnetic effect of current to function? Now, when we take a look at the options here, we see for option D, a telephone receiver converts electric signals into sound, and it does this by electromagnetic induction. So it works with the magnetic effect of current as well. So now option C says a moving coil galvanometer, which is an instrument that measures current by magnetic effect. So it looks at the interaction between current and magnetic field to be able to measure the current in a conductor. So it relies on magnetic effect as well. Option B is an electric bell which attracts the hammer to continuously hit the bell by using its magnetic field. So it relies on the magnetic effect as well. But the lead acid accumulator delivers current from chemical energy. So it does not rely on magnetic effect at all. So the correct option for this question is option A. A charged particle is moving in a uniform magnetic field. If the direction of the motion of the charged particle is parallel to the magnetic field, the path of the charge will. Now, what we have to pay attention to here is the direction of the charged particle, and we are told that the direction of the motion of the charged particle is parallel. Now, because it's parallel, that it's either 0 degrees or 180 degrees to the magnetic field. So as a result, if you apply the force of a magnetic field, BVQ sine theta, here theta is 0 or 180 degrees, which will give you 0 as well. And by the time you multiply, you see that there's no force acting on the charged particle. Now, if it were perpendicular on the other hand, it's going to feel the maximum effect of the magnetic field, which will then force that charged particle to begin to move in an elliptical orbit around the direction of the magnetic field. So, but because now it is parallel, there will be no force, so it will continue along that same path, which is in a straight line. So the correct answer here is option A. If you're yet to be subscribed to the channel, kindly take a second of your time to hit the subscribe button and also click the notification bell icon so that you get alerted every time we put out a new content. And please don't forget to download the Exam Fun app. And in order to infuse a bit of fun into your study time, please click the link in the description box of this video to download the Exam Fun app today. And do not forget that we are here for you if you have any question at all, perhaps on what we are doing presently, or something you found during your study time that you would like some help with. Kindly put your questions in the comment section and we will definitely attend to all of your questions. And please don't forget to like and share the videos so that we can continue to reach more audience who are in need of content like this. This question says, lodestone is a natural magnet. It points at, now magnets when suspended freely should point north-south. And of course we have natural magnet and artificial magnet. Lodestone is an example of a natural magnet. It is an object that has magnetic property that is found in nature. And when you suspend it freely, it always aligns with the north and south direction. So it points north-south when it is suspended freely. So the correct answer to this question is therefore option B. What is the best method of demagnetizing a steel bar magnet? Now, demagnetization is a process where you cause a magnetic material to lose its magnetic property. Now, this is for artificial magnets. Now, when it comes to artificial magnets, we have temporal magnets and we have permanent magnets. The temporal magnets are made of soft iron, while the permanent magnets are made of steel. So when it comes to the temporal magnet, they can easily be demagnetized. So for the temporal magnets made of soft iron, you can demagnetize it either by hammering, by heating it, and even just generally handling it roughly can cause it to lose its magnetic property. However, when it comes to permanent magnets made of steel, they are difficult to magnetize, but once they get magnetized, it is also very difficult to demagnetize them. So in order to demagnetize them, hammering, hitting it or rough handling it, yes, may cause it to lose some of its magnetic property, but it is not sufficient. The best way to cause steel magnets to lose their magnetic property is by the solenoid method. So to answer this question, the best method to demagnetize a steel bar magnet, which is a permanent magnet, is by the solenoid method, which is option D. The magnetic force on a charged particle moving with a velocity v is, now When we consider the force on a charged particle in a magnetic field, F is given by Q V B sine theta. Now, in this case, the constant of proportionality depends on the magnetic flux density and the direction of the charge with respect to the magnetic field. So that is B sine theta are constant. So that tells us that F is proportional to Q and V. So that is, it is proportional to the charge and the velocity. So when we consider that, we see option A say proportional to both the magnitude of the charge and the velocity. So that makes it the correct option. So we go with A. The force on a current carrying conductor in a magnetic field is greatest when now let's recall that equation. F equals Q V B sine theta. So where theta here is the direction of the current carrying conductor with respect to the magnetic field. So now let's consider the options. A says conductor makes an angle of 60 degrees. Now at 60 degrees, sine 60 is going to give us about 3/2. Now, when you work with that, that is going to give you 0.866666 like that. So, and when you multiply this by 0.866, it's going to drop the force by a certain value. Now, let's consider option B. Option B says force is independent of the angles between the field and the conductor. Now, that is false because we see that the angle comes into consideration even in the equation linking the force and the magnetic field. Now, option C says when the conductor is parallel to the field. Now, if the conductor is parallel to the field, that is the angle there is either 0 or 180. That is whether it is parallel or anti-parallel. So if you plug that in into theta, you're going to get 0 or -0, which will of course make the force acting there 0. So that means it cannot be greatest at that point. So that leaves us with option D, which says the conductor is at right angle, which is 90 degrees. And when you put in 90 degrees, so 90 is going to give you 1. That is, the highest value of the force you can get is that when the angle is 90, that is when the conductor is at right angle with the field. So the correct answer is option D. Steel is more suitable for permanent magnets than iron because the former, now by former here it refers to steel, not the iron. If they had used the word latter here, that would have been that we are referring to iron. So please take note of that statement there. So we are looking at why steel is more suitable as a permanent magnet. Now, one thing we know is that to magnetize a steel is not as easy as it is to magnetize soft iron. However, the reason why it is more preferred is because it forms a permanent magnet in the end. That is, it retains its magnetism very long even after the iron has lost its own magnetism. So when we consider the options provided, option A says it's easily demagnetized by shaking vigorously. That is wrong. It's only soft iron that can be demagnetized that easily. Now, B says it's an alloy of many materials. Yes, steel is an alloy, but this is not the reason why it is more preferred as a permanent magnet. C says it's easily magnetized by alternating current through one circle. Now, this is wrong. It takes more than one circle to magnetize steel. And then finally, D says retains magnetism more than iron, which is actually the reason why it is called a permanent magnet. So that means the correct answer is D. A straight wire 15 centimeters long carrying a current of 6.0 amperes is in a uniform field of 0.40 teslas. What is the force on the wire when it is at right angle to the field? In this question, we see that L is given as 15 centimeters, which is 0.15 meters, which is the correct SI unit. The current I is given as 6.0 amperes. And then we are seeing that the magnetic flux is given as 0.40 teslas. And then we are asked to find the force, given that the angle is 90 degrees because it is at right angle to the field. Now, we have already seen the case where we said F equals BVQ sine theta, but you should also know it's the same thing as BIL sine theta. Now, for more explanation on how we can derive this equation, please check out the video on this channel for magnet and magnetic field. We explain that in more details there, but please take note that these two equations are the same and they can be derived one from the other. They are directly linked. So, because we are working with current and length of the conductor, we're going to be using this other side of the equation. But whenever you are working with velocity and then the charge, you're going to be working with BVQ sine theta. So to work with this, we can then say the force equals B, which is the magnetic flux intensity, that's 0.40, multiplied by the current, that's 6.0, multiplied by the length, which is 0.15, and then multiplied by sine 90 degrees. Sine 90 degrees is 1. So the force is therefore 0.40 times 6.0 times 0.15 times 1. That means the force here will give us 0.36 newtons. So the correct option here is C. The north pole of a magnet can never be separated from the south pole because of the property known as. Now, sometimes you may try to cut a magnet to see whether you can isolate it. Like if you take a magnet like this, a bar magnet that has north and south at the extreme ends like this, and then you break it like this. What is going to happen is that the electrons are just going to be redistributed. Instead of isolating the poles, it will redistribute the electrons, thereby creating what is known as a magnetic dipole. So as a result, when this becomes north, the other end that is cut off from it will now become the south, and then this other part will then become north, and then continues like this when this is south. So you see, just creates a magnetic dipole. And there has never been any found evidence of what is known as the magnetic monopole. So it means that it cannot exist having just one pole. It must have north and south. So the reason why you can't separate this is due to a property known as magnetic dipole, which is in option C. The force on a charge moving with a velocity v in a magnetic field B is half of the maximum force when the angle between V and B is. Now, to get the maximum force, in the case of maximum force, at max force, theta equals 90 degrees because F equals BVQ sine theta. And if you plug in 90 degrees here, you're going to get BVQ. So, which implies that F equals BVQ. So, in order to get half of that, what we have to apply is that F over 2 will now be what? BVQ sine theta. Remember, this is F. So, that is F over 2 equals F sine theta. F cancels out. So this implies that sine theta equals half. So now that we have established that sine theta is half, let's find the angle then. So theta then becomes sine inverse of half, and that will give us 30 degrees. So the correct answer here is option C. Now don't forget to put in more practice by studying with the Exam Fun app. The app is created to infuse a bit of fun into your study time as you get to answer questions on any subject of your choice at different levels, and then you get points as well as earn some bit of money. So it is both exciting and rewarding. You can find a link to download the app in the description box of this video. Kindly click the link to download the app either from the Google Play Store or from the Apple Store, depending on the device that you're using, and then get in some fun as you learn today. And please don't forget to be subscribed to the channel. If you are not yet subscribed, please click the subscription button and the notification bell icon so that you get notified every time we put out a new content. And please keep liking the videos, keep sharing them, and don't forget that we are here for you. So if you have any question at all, whether it's on what we are doing presently or it's on something you found during your study time that you would like some help with, please send your questions, drop them in the comment sections of the videos, and we will definitely attend to all of your questions. So let me say a big thank you to all of you who have been part of the series so far. This comes to the end of day 33. The series still continues. So I'll be seeing you in the next video. But bye for now.